Hello, everybody. Sorry for the slight delay, but we are ready to go. My name is Rich Ottinger, and I'm the Marketing Programs Manager for Park Systems. Welcome to the second installment of Park Systems 2019 Material Science Research and AFM webinar series. Today's presentation is titled New Surfactant Design. Before we begin, let me give you a quick overview of today's session. The presentation is expected to take approximately 40 to 45 minutes, which should allow us some time for a question and answer period at the end. If you click the raise your hand button at that time, I can unmute your line for you to ask a question. If you would prefer, you may type in your questions at any time during the webinar, and I will try to pose those at the end. Any questions we do not get to, we will try to address in a follow-up email. It is now my pleasure to introduce you to Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He is a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please welcome Dr. Rigoberto Advincula.
Thank you, Richard, and I'm happy to give this webinar on new surfactant design and developments. And hopefully a number of you will have opportunity to ask some questions on the top for today. And just like what Richard mentioned, I'm a professor at Case Western Reserve University, a comprehensive university located in Cleveland, Ohio, very cultural part of Ohio. We have the Cleveland Museum, Cleveland Orchestra, and we're also home to ThinkBox, one of the first makerspace additive manufacturing design and engineering facility in a major research university. So this is a picture of our building, macromolecular science engineering building, and acknowledgement to my group members as well. So we do a lot of research on different types of interfacial chemistry, interfacial modification, nanostructuring, use of surface sensitive analytical methods such as the AFM, and we use different types of nanomaterials as well to produce different applications like composites, nanocomposites, sensors, modification, rheology modifiers, modification of viscoelastic surfactants, and so on. But today, of course, we will focus on the use of surface science based on surfactant chemistry. So let's get on with the meat of the talk. I'm going to give you an overview, of course, about the basic surfactant design, some of the common surfactant hydrophobes and hydrophiles. And then we will go on into looking at different unconventional surfactant designs, polymeric surfactants, bio-derived surfactants, linear, nonlinear surfactants, and possible applications in consumer products, oil and gas chemistry, paints and coatings, etc. So why the emphasis on surfactants? Well, even before we focus on the industrial application, surfactants, of course, is essential for life. And this is what constitutes, for example, your cell membrane. This is what constitutes the surfactants in your lungs that allows you to breathe normally. And of course, surfactants found in many applications from detergents, cosmetics, pharmaceutical, textile, fiber, plastic composites, metal processing, almost makes them ubiquitous that we don't pay attention to what they do because they simply work, or sometimes they can be a problem. In the case of oil and gas, there's a lot of natural surfactants that we call them asphaltene that can mess up a pipeline in an oil storage and transport value chain. So a typical surfactant and its characteristics are based on their application. So for example, when we talk about detergency, we are concerned with the critical micelle concentration, its stability in different pH, salt conditions, biodegradability. Emulsification is used a lot in the food industry, but as well as different environmental and biological applications, including cleanup, lubrication. We use surfactants and their properties to adsorb on surfaces, metal surfaces, chemical stability. In mining, A lot of them is, of course, is used in mineral flotation, flocculation, petroleum recovery. A lot of them is used actually in emulsification as well, and also in terms of enhanced oil recovery and even hydrofracturing fluid. And then finally, with pharmaceuticals, they are used as surfactant drug excipients, emulsifying properties, and valued for their biocompatibility. So the relationship between its application is really a structure property or a structure composition property proposition. That means you need to know the structure of the surfactant, its effectiveness in its given intended application, or even the design so that you can produce it commercially as well. And some of the important characterization of surfactants when they go from laboratory to production, of course, one pays attention to their HLB or hydrophobic lipophilic balance. A basic measurement is based on surface tension measurements, determining the critical micelle concentration through a number of methods, including light scattering, ion conductivity, detergency power, wetting control, foaming reduction or capability, etc. So in other words, a universal surfactant has many, many uses, especially if they can be derived from sources such as oleic acids or fatty acids. A basic surfactant design, or so surfactant is a word that is a contraction of two words, surface active agent, surfactant. A typical design or building block is, of course, the hydrophobic part. Typically, it's an alkyl chain, and a hydrophilic part, which can be anionic, cationic, zwitterionic, or even non-ionic. So the balance of these two parts makes for what we call an amphiphile or amphiphilic. And here you can see that a typical hydrophilic, so when we say hydrophilic group, it is water-loving or water-soluble. A hydrophobic group or hydrophobe is a water-hating or you would say it's oleophilic or oil-loving. So the composition of these two or the balance of these two makes up for your surfactant. Now, typically a surfactant can be classified based on the head group. It can be anionic, so the most common ones are based on sodium dodecyl sulfate or SDS. Cationic, it can be cetrimonium bromide or CTAB. Zwitterionic could be based on the betaine or sultanes. And of course, lipids are non-zwitterionic. And the non-ionic are essentially neutral, and a lot of them are polymer-based, such as the polyethylene glycol alkyl ethers. Here you can see the importance of the critical micelle concentration. CMC basically allows us to characterize when the micelle forms. The micelle basically is a aggregate, a dynamic aggregate of surfactants that are stabilized in solution versus that of surfactants at the air-water interface. Therefore, you need a minimum amount of micelle to form this surfactant to form this micelle to achieve micellization. And this can be done by measuring properties such as the surface tension, ionic conductivity, or size directly from light scattering. And we will not have time to review the different methods of surfactant measurement systems as well. However, a micelle can be extended to beyond spherical to worm-like micelles, to vesicles, bilayers. Essentially, these are what we call liquid crystalline mesophases or even lyotrophic phases. That is a result of increasing concentration or the change in the geometry of the surfactant based on what we call the packing parameter. The critical packing parameter is characterized by the volume of the hydrophobic part, the optimal surface area occupied by the head group, and the critical length of the hydrophobic tail. So if you combine this, you can get the packing parameter, which actually defines its ability to form these various phases or hierarchical ordering. And here you can see again some surfactants based on sweeter ionic, anionic, non-ionic that can constitute various critical packing parameter arrangements. In fact, you can use TEM, transmission electron microscopy, to directly observe these vesicles or micelles effectively. So going on with the basics of a surfactant design, one is you first conceive the desired structure, hence trying to understand the packing parameter. Second, you gather together the various types of blocks that you can commercially obtain or synthesize. Typically in a commercial application, you of course want something that is inexpensive or can be derived commercially with the available supply chain. And then, of course, you synthesize or put them together. And of course, this is not a hard thing to do given the amount of or variety of commercially available surfactants out there. So typical head groups or hydrophilic part could be anionic, and most common will be the carboxylate or carboxyl, the sulfonates, the sulfates, the phosphates. Cationic, a lot of them are based on quaternary ammonium halides and sometimes imidazolinium derivatives. Non-ionic, typically we will not label amphiphilic here based on sweeter ions. We can discuss more of that. But a lot of them are water-soluble polymers such as polyoxyethylene or polyethylene glycol. Now, a typical hydrophobe will be a straight chain alkyl group. It can be anywhere from C8 to C22. It can be a branch chain alkyl group through internal substitution. It can be an unsaturated alkyl chain, meaning it has a double bond, such as those derived from a vegetable oil, or it can be an alkyl benzene with various substitutions and pattern. And of course, other variations can include siloxane or fluorinated or perfluorinated alkyl chains. As you can see here, a perfluorinated alkyl chain can lend itself to ultraphobic properties. Polydimethylsiloxane derivatives can be good demulsifiers, or even long chain polymer, polyethylene glycol, polyoxypropylene, and so on. And then a number of biosurfactants are basically derived from bio-based feedstocks or even typical lipids. So here you can see that surfactant family tree essentially allows you to take a alkyl chain. One can modify it by sulfonation or a halide. The halide group makes it susceptible to quaternary amidation, such that you get your cationic surfactants. On the other hand, an alkyl chain can be derived to have an alcohol group. An alcohol group can be further oxidized to form your fatty acids, longer chain alcohols, or other sulfates and sulfonate derivatives. And in fact, some of these are the most common routes by which synthetic derived surfactants or even petroleum-based surfactants are obtained. Here you have a summary of the most common encountered hydrophilic groups that are commercially available. And this will be good exercise for you to remember what a sulfonate structure looks like: a sulfate, carboxylate, phosphate, etc. Now, typically this contains a counter ion or Gigan ion. The counter ion balances electrostatically the ionic head group. Similarly, you have positively charged surfactants, ammonium, quaternary ammonium, with their halide counter ions. And then you have the sweeter ionic betanes, sulfobetanes. Not shown here are the sultanes, etc. The non-ionic surfactants, polyoxyethylene, or derivatives of polyoxyethylene to have a sulfate group, polyols, sucrose esters, and so on. So these are some of your typical hydrophilic head groups. Now, along the family tree, one may ask, well, where do most common surfactants come from? You have a variety of choices. They can be from natural fats or oleofats. They will end up to become your fatty acids. The fatty acids can be derivative to produce amine and amine oxides. A good number of natural fats or fatty acids or ethylene-derived surfactants are found in a lot of common detergent or soap ingredients. So ethylene allows you to produce ethylene oxide and therefore polyethylene oxide, which becomes your alcohol ether sulfates as well. On the paraffin sides, benzene and paraffin, these are your synthetic waxes. Paraffin or paraffin wax derived can become your linear alpha olefins, which can be sulfonated, or a secondary alkyl sulfonate as well. On the other hand, a benzene plus a linear paraffin will give you your alkyl benzene sulfonates. Again, another common commercial surfactant. So this evolutionary pathway, of course, can be modified so that you can have other commercially viable routes to new surfactants. I will not be able to discuss here other types of surfactants based on 2-alkyl chains or 3-alkyl chains or modification of the fatty esters. That can be reserved, but rather I'll be focusing, of course, on some new surfactant designs. Now, in terms of what is available in industry, a majority of the surfactants out there are basically anionic surfactants. And then you have the non-ionic surfactants, and a minority type will be your cationic surfactants. Now, this translates to surfaces. In fact, one can say that a majority of the surfaces you will encounter is actually negatively charged because of the anionic surfactant predominance in commercially available types of application. Now, let's talk about a zwitterionic surfactant or an amphoteric surfactant. A zwitterionic surfactant has both a positive and negatively charged. So they are electrostatically neutral, quote unquote, although the balance of the negative and positive charge can bias this towards anionic or cationic form. And worldwide, zwitterionic surfactants are not widely produced, yet they're very effective, especially in applications requiring high thermal and chemical stability. Shown here is a structure of the zwitterionic surfactant alkyl betaine. Betaine has a combination of the ammonium group and the carboxylate group. So other types of derivatives, it can be amine base, amine carboxylic acid, preamine. It can be based on imidazoline derivatives, quaternary ammonium carboxylic combination. It can be an amine sulfonic acid giving you your sulfate ester, or quaternary ammonium sulfonic acid. And sometimes we just call them sultanes, sulfanes, sulfobetanes, etc. Here again are some of the combinations of betaine. Betaine surfactants are some of the most common and commercially available zwitterionic surfactants. The interesting thing with these zwitterionic surfactants is that they can behave stable in a stable manner, even in their micellization, at a high or low pH condition, and thus they are highly valued for high performance applications, very good detergency, anti-static agents, fabric softeners, and so on. Okay. Other types of surfactants based on phosphatides and phosphates, phosphonates. Okay. Lecithin, for example, is a good example of a phosphatidyl type of surfactant. Lecithin we get from, or lipids we get abundantly from egg yolk, cottonseed, sunflower, and soybean oil. Now, let's talk about unconventional surfactant design. A polymer surfactant, just as what it says, is derived from a macromolecule. A biosurfactant can be derived from microorganisms or bio-based feedstocks. A nonlinear surfactant or an unconventional nanoparticle surfactant, and their applications in viscoelastic surfactants. So basically, this is some of the unconventional designs and theme that I'm going to finish this talk. So let's talk about polymers and why it's so important to use them as surfactants. As you can see here, a polymer or macromolecule is able to order, self-assemble on surfaces. Flat surfaces, modification in layers, eventually macroscopic properties, or the application of polymers towards gelation, Pickering emulsion, different types of cross-linking and hydrogel type of systems. In other words, a polymer is actually a nanomaterial that has surfactant capabilities. Now, a lot of these are based on copolymer type of arrangements. A predominant type of copolymer that is used as a surfactant are the block copolymer linear systems. And block copolymers are, of course, found in compatibilizers, additives, elastomers. They have interesting mesophases in which you can order the chain length and the molecular weight to produce different phases such as cylindrical, lamellar, spherical, and so on. But synthetically, one can have a hydrophilic block and a hydrophobic block. One can synthesize a diblock, a triblock, a star copolymer branch, or a linear branch. All of this makes up for a very interesting phase behavior or surfactant stability as well. In fact, polymers are considered very stable surfactants versus that of small molecule surfactants. In other words, polymers can be used at a higher temperature, pressure, or conditions that a normal small molecule surfactant will easily degrade or have a lot of dynamic properties. Now let's talk about biosurfactants. So for simplicity, when we say biosurfactant, it simply means a surfactant derived from a natural source. Typically, this comes from plants, animals, or extraction from microbial cells, and the separation procedure simply involves extraction, precipitation, and distillation. And a lot of them, of course, are appeal in terms of sustainability or use of natural derived surfactants versus that of synthetic and petro-based surfactants. They are typically non-toxic and therefore are preferred in some application, and they are found in, as I said, plant, animal, and microbial sources. So let's look first at the glycol lipids. When we say glycol lipid, it's a polysaccharide or a carbohydrate attached to a fatty acid. Depending on its source or the carbohydrate moiety, glycolipids can be classified as sophorolipids, rhamnolipids, and trehalose lipids. And this is based on the type of polysaccharide attached to your lipid or to your surfactant. Then we have the proteolipids. As it says, it has proteins or polypeptides on the hydrophilic moiety. And then typically a polymer itself, whether it's glycolipid, protein, or polysaccharide, or other polymer biomolecules or biomacromolecules are surfactants, but of a high molecular weight variety. Okay, so biosurfactants can be derived by extraction directly from plants and animals. However, certain enzymes or microbes are programmed, quote unquote, to produce different surfactants. This can be based on genetic engineering and harvested as well in a bioreactor. So for example, some of these bio-based surfactants can be programmed to have the presence of carbon, nitrogen, or even multivalent cations. So a microorganism, for example, will produce the surfactants, and essentially with a bioreactor, you then harvest them separately from the microorganisms. So you first, in a bioreactor, you need a media, you need a fermentation a procedure, and then product recovery. And here are some examples of biosurfactants and the organism that they were derived, and the substrate source, and the charge, as well as their surface tension. So biosurfactants, of course, are used in a number of applications. They can be used for heavy metal remediation, pathogenesis. They can be derived to become potent antibiotics, especially the quaternary amine-containing derivatives. And this can be used also for different types of agriculture or agri-based harvesting and biofermentation. Let me skip that and look at this chart here. So, for example, a surfactant like the rhamnolipid can be used to remove styrene from contaminated soil. This was, for example, found in this paper. Styrene, of course, is a monomer used to make polystyrene or petroleum-based polymer. And this is a demonstration that it can be used for remediation or bioremediation to remove a styrene or even other PCB type of contaminants. Okay, let me skip this and focus on the other remaining unconventional polymers. So let's look at specific class of black copolymers called linear dendritic or arboreal systems. So a dendrimer is a hyperbranch macromolecule. Essentially, it's a large molecule with a lot of branching, controlled branching, that is. And by generation or functionality, you can separate their constitution. They can be made by divergent or convergent methods. So it's like that of marrying a tree with a alkyl or polymeric linear chain. So the linear dendritic family resembles that of, let's say, a tree, as you can see here. You will have a corona leaf, which is your functional peripheral group. Now, that functional peripheral group or highly branched group can either be a hydrophilic or a hydrophobic part. In this example, for what you have is a third generation monodendron based on a polyester, but with a polyethylene glycol methoxy-terminated linear group. Now, it will surprise you that in this case, the hydrophilic group is actually the linear part, and the hydrophobic group is the dendrimer part. So as you can see here, the synthesis of linear dendritic systems can involve a linear dendrimer growth based on a convergent synthesis, or simply a linear polymer attached to a hyperbranch system, which is not topologically exact. Now, the linear hyperbranch system is actually preferred because it is easier to synthesize, less expensive to synthesize than a topologically exact linear dendron block. Now, there are several strategies to make this type of surfactants. One can have a coupling strategy in which you have a linear part that is attached to the branch part, or you can have a chain-first strategy in which the macro initiator allows for the growth of the dendron, let's say by divergent methods, or we have the dendron-first strategy, meaning the macro initiator is actually a dendrimer. The linear polymer grows by addition polymerization on the branch. And that means that this type of linear dendrimer block copolymers can be accessed through 3 different methods. Interestingly, they form also very good mesophases that can be observed by atomic force microscopy or transmission electron microscopy, as exhibited by this image based on a polystyrene, polybutadiene block and a polyethylene oxide PCS block with a dendron as well. Here you can see other types of mesophases obtained by transmission electron microscopy, atomic force microscopy, and evaluation by small angle X-ray scattering to look at their periodicity. Potential application of linear dendrimer diblock of polymers. A lot of them I've seen as useful for drug delivery systems, drug carriers. They can be used to form what we call semi-interpenetrating networks and even hosts for crystallization and biomineralization processes. Some of them have been used for electrochemistry or photoluminescence. Why? Because the big head group or the dendrimeric group can have a very high density of functional groups, including dyes, and the linear polymer can be a conducting polymer as well. Now, the other type of surfactant, which typically we would just call a colloidal nanoparticle with a Janus behavior, has been reported and is useful for high temperature stable applications. In a bulk exchange particle, if it has the ability to rearrange where, let's say, the hydrophilic group prefers one side and the hydrophobic appears on the other side, then what we end up is a Janus particle after the Roman God Janus, or two-phase, looking forward, looking backward, or simply two-phase. Now, the nanoparticle itself, in fact, nanoclay, graphene, silica nanoparticles can behave as effective surfactants. It can modify surfaces. It can be used to form Pickering emulsions. And they can be observed or produced even using microfluidics. So take this case of a bisfunctionalized Janus dendrimer, where you have a polymer particle or polymer Janus nanoparticle, the hydrophobic part exhibited by the long alkyl chain, and the hydrophilic part consisting that of alcohol-terminated polyester dendrimer. A cylindrical polymer brush is also possible. Here you have a linear polymer that is accessed by ring opening metathesis polymerization, followed by the addition of a methacrylate or acrylate derivative on the alkyl group. Janus particles based on polyacrylic acid and polyethylene oxide, or polyacrylic acid and polyvinyl pyridine has been observed as shown here. It can have various phases of the micelle, and the block behaving that of a Janus distinguishes between the hydrophilic and hydrophobic part. Here you can see a tri-block terpolymer that tends to self-assemble and form what clover type of particles, or here you have this cross-linking resulting in a Janus micelle that has been observed by TEM. Here you can see a Janus nanoparticle that was actually derived either by microfabrication or modification of silica. They can be used for different printing methods to create patterns on the surface, or here you can see the modification of a silica particle to have a hydrophobic and hydrophilic block based on its synthesis in a wax emulsion type of method. Now, the last topic for today is based on viscoelastic surfactants. Now, viscoelastic surfactants are finding increasing use as a viscosity modifier. This can be derived from using higher concentrations of surfactants, so basically beyond the CMC, to form rod-like micelles. The rod-like micelles or worm-like micelles increase in length, and based on entanglement or preventing actually from entanglement, it increases the viscosity dramatically. That's why we call this viscoelastic surfactants. It has properties that shift from a low viscosity fluid to a gel-like behavior simply by controlling the dynamic properties of the surfactant, but for sure a much higher concentration than your CMC. So as you can see here, rheology is a very important tool to investigate these viscoelastic surfactants. One can measure or correlate the concentration with the change in viscosity. Very often we apply rheology, which is measuring the dynamic behavior or nonlinear behavior. We basically get the storage or the loss modulus, which we sometimes call G prime and G double prime. And we can observe based on the concentration or changes in the pressure or temperature how these viscoelastic surfactants vary. So here you can see some of the surfactants that are commonly used. CTAB, sodium dodecyl sulfate, other types of non-ionic surfactants are included. And again, what happens is that you have spherical micelles that have much higher concentration, produce your worm-like micelles. And in fact, if your concentration is too high, you end up with a crystalline or polycrystalline phase. Now, viscoelastic surfactants are finding increasing use beyond that of cosmetic products. It has been used for oil and gas stimulation or well stimulation application or oil chemicals. It has also been used as lubricants and substitution for BTEX type or other types of organic solvents. So believe it or not, the time has passed quickly. I'm just going to summarize some of the traditional and non-traditional applications. Surfactants, easiest that comes into mind are detergents and cleaners. They're used a lot in cosmetics and personal care products. Think about your shampoo this morning. Textiles and fibers, dyeing textiles or modifying surface of fibers is important. Leathers and furs or conditioning of different types of leather products. Of course, paints, lacquers, and other products. Paints in particular uses a lot of surfactants to produce what we call latex or emulsion polymers, which are your acrylate paints. They're used a lot in the paper industry, modification of other cellulose products, including blown film. Of course, they are used a lot in the mining or flotation or recovery, metal processing industries such as lubricants and cooling emulsions. And I can go on and describe to you a variety of new uses of surfactants. But suffice it to say, I'd like to give some time for questions and answers. So with that, I'd like to end this talk and thank you for your attention.
We are back up and running. We do have a few questions. The first for you is, what are Gemini surfactants?
Yes, Gemini surfactants are surfactants with, let's say, two alkyl groups or two head groups. And that means that you have a surfactant that is vicinal or geminal, but essentially you can have either two alkyl groups or two head groups. And they are more effective and more stable at times, and in fact they are preferred in some applications, but they are harder to synthesize.
Okay. I have one other question on the screen so far. If anybody else has a question, you can type it in or raise your hand, and I will unmute your line when we get a moment. This next question is from Richard Harper. Can AFM analyze surfactants in a solid matrix cross-section?
Yes, of course. It depends on the technique that you employ. The use of transmission electron microscopy, of course, is an option. Atomic force microscopy is gaining ground. We have used AFM in methods like Langmuir-Blodgett films of polycrystalline surfactants. If you're looking at a cross section, then obviously there has to be a way to fix the surfactant arrangement, let's say in a cross section manner. And that means that you may have to go to what we call STM or high vacuum modes to do it. And AFM, of course, can go all the way to the atomic scale, in which crystalline phases, let's say found in gold 111 surfaces, actually allows you to measure the periodicity or distance between alkyl chains. So without further knowing what you intend with this type of measurements, whether you're interested in solid state behavior or actual detergency, there are a number of options, and certainly between TEM and atomic force microscopy, there are a variety of options, including applications of tribology or lateral force microscopy to measure the ability of surfactant to adsorb at surfaces.
Okay, I don't see any other questions right now. So
yes, Richard. Yeah, I would like to follow up that. Of course, we have this webinar series that some of you subscribe, and we will have the opportunity in months to come to have a variety of topics covered. First of all, I'd like to thank Park Systems for the opportunity to give this webinar series. But at any point, if you have questions, I can direct you to send me an email at rca41@case.edu, or you can simply go to the department website and look for my name. So I'd be happy to hear from you, correspond with you, answer your questions if this particular webinar is of interest, and other topics. I will be happy to correspond with you.
Great. And we do have one more question that came in, so I'll just ask that. Is there an advantage to having a mixture of surfactants instead of a single surfactant?
The answer is yes. The process of, let's say, using viscoelastic surfactants or emulsion sometimes means that you need to look at the dynamic behavior between different pH, temperature, or even pressure conditions. Surfactants, in cases where we use them for emulsions or viscoelastic surfactants, can have what we call co-surfactants. Now, co-surfactants can either be a smaller molecule, or it can be a surfactant which has a number of unsaturated groups. It can be a bulky group. And in fact, in nature, or what we'll find, let's say, in cell membranes, is actually a mixture of surfactants. So yes, the answer is mixed surfactants have an important role on the application, as well as trying to disturb or modify the packing behavior of, let's say, a straight and linear alkyl surfactant by the addition of other types of geometries or surfactants with various packing parameters. May I suggest that one of the tools that can be actually used to investigate mixed surfactant behavior is Langmuir-Blodgett studies at the air-water interface, because this gives you a direct correlation on the surface tension change or surface pressure area isotherm change as a function of mixed surfactant composition. Okay, or percentages. So the technique is called Langmuir-Blodgett film device.
Excellent. I just want to let everybody know that this webinar, the video will be posted in a few days on our website at parksystems.com. So you'll be able to watch that there and share it with anybody that you think might be interested going forward. It'll be on our YouTube page as well. I have one last question I'll take this opportunity to ask, and that is, can you give us a brief preview of next month's webinar topic, viscoelastic surfactants and oilfield chemicals?
Very good, Richard. Thank you for reminding me. And viscoelastic surfactant is a direct offshoot of this webinar today, in that I will be talking about viscoelastic surfactants, how it is formed, the theory behind it, methods of measurements, its application, especially in the oilfield chemical industries as well. So please tune to our next webinar, and you're going to learn more about VES, or Viscoelastic Surfactants.
All right, thank you very much, Doctor. Please join us for that session. That's Wednesday, March 20th, once again at noon Eastern Daylight Time. And thank you all for joining us for this session of Park Systems 2019 Material Science Research and AFM webinar series. You can find more information about Park Systems AFM at parksystems.com. And please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series, feel free to reach out to me directly at richard@parksystems.com. Thanks again, and we hope to see you all next month.